Hello everyone, this is Dr. Young, and in this video I'm going to start to introduce to you these ionic reactions, the SN1, SN2, E1, and E2 reactions, which all kind of go hand in hand because they're all competing with one another. And so this portion tends to be sort of difficult for students at first because it seems like there's 1,000 different factors and you need to memorize all of them. But once you kind of get the main driving forces behind these mechanisms, it's not so bad to parse them out. So first I want to introduce some basic concepts so we got some terminology down, and then in the next video I'm going to start introducing the SN2 and the SN1 videos. So first of all, right, like I said, these are the SN1, SN2, E1, E2 reactions. And what we're going to see is that are all going to involve some sort of substrate, which is going to be our alkyl halide, or we'll see later a sulfonate ester. And they're going to involve some sort of nucleophile or base, right? So we need to kind of talk about what's a nucleophile and what's an alkyl halide. Now, alkyl halides, you may or may not already know. You should already know that an alkyl halide, right, it's just something with the halogen on it. So, right, the alkyl piece just means that we're talking about some sort of hydrocarbon group. So let me write hydrocarbon here. All right, so it's going to be some sort of hydrocarbon piece. And usually it's, it is sp3 at that point of attachment. If it's sp or sp2, then it's a different group, and we're not talking about those sorts of things. Then it would be alkenyl or something like that, or you'd have an alkyne there. So we're talking about sp3 hybridized carbons and just hydrocarbons, right? Now for the halide piece, stay. We're talking about the halide piece here, right? We're just talking about halogens. Right, so halogens, your good old halogens, which you may have seen before, but they're abbreviated just generically as X, so that whole group. If you see something like Rx, that R group, right, is just the residue group, the residual group, that's just some sort of organic piece, and then X would mean that there's a halogen there. And the halogens that we're talking about here are fluorine, chlorine, bromine, or iodine, right? Those are our big four halogens. And what we want to do is we want to be able to look at an alkyl halide, a haloalkane, and categorize it as either being methyl primary, secondary, tertiary, or quaternary. And that's just referring to how substituted the carbon is that halogen is on, right? So we want to ask ourselves how substituted is the carbon that the halogen is attached to. Right, so like for example, in this one right here with the bromine, right, it's attached to this carbon right here. And so I want to ask myself, how substituted is that carbon, right? How many groups, right? When we're saying about how substituted, what we're saying here is how many carbon groups. We want to know the number of carbon groups attached. Not the total number of carbons if it's some long chain, but just the fact that that carbon is attached to more carbons. So for example, if I was looking at this one with the bromine, I'd see that red dot, right, that's where the bromine's attached. I see that it's attached to 2 different carbon groups. So I'd say then that is a secondary carbon. Since it's attached to 2 carbon groups, right, it's a secondary carbon. And as shorthand, you'll see sort of the number 2 and then a degree sign. We never say it's like 2 degrees. We say that that's secondary, right? That's supposed to mean secondary. So that would be a secondary alkyl halide. If I go and I look at the second one, right, the chlorine's on this carbon, that carbon's only attached to 1 other carbon, so that would be a primary, right, 1, and then that degree sign, so that'd be a primary carbon, that'd be a primary alkyl halide or a primary haloalkane. If you go and you see something where the bromine, right, is only on this carbon, the bromine's on that carbon, and there are no other carbons, so that would just be a methyl, right? Because that's all that's really attached there is just a methyl group. So we'd call that a methyl halide. And there is no other symbol for that. We just read out methyl. It's a methyl halide. That'd be a methyl alkyl halide. Moving on to the fourth one. I mean, you can pause at any moment here. You can probably do the third and the fourth one on your own. But if you look at the fourth one here, right, the fluorine is on this carbon. Let me highlight that. Is on this carbon. And if I look at that carbon, there's 1, 2, 3 carbon groups coming off of it, which means that that'd be a tertiary alkyl halide. Tertiary halide. And then lastly, for this one over here with the iodine, it looks like this carbon's only attached to one other carbon, so this would be an example of a primary alkyl halide. And you may have heard these terms before, right? Primary, secondary, tertiary, etc. They just refer to how substituted something is. And in the case of alkyl halides, we're asking how substituted is the carbon that they're attached to. And what we're going to see in the next video is that it makes a big difference on whether, on how easy is it for a nucleophile to approach, right? If it's primary or methyl, there's not a lot of carbon groups on there, so it's really easy to approach. If it's tertiary, there's a whole bunch of stuff there. There's 3 other groups there. There's a lot more steric hindrance, and so it's harder for a nucleophile to approach. And so we're going to start categorizing our SN1, SN2, E1, E2 reactions by what types of substrates they work out with. So that's one half of our equation here, is that we need to know what's going on with our alkyl halides. What type of alkyl halide do we have? We also need to look at, though, what type of nucleophile we have. Do we have a nucleophile? Do we have an electrophile? What do we have? So let's talk about that. Right, so like we said, these reactions involve alkyl halides or a nucleophile, and a nucleophile or base. And so in this video, for the last part of this, I just want to go over the difference between a nucleophile and electrophile. And again, depending on what order you're watching this video in, if you've already learned stuff about alkenes, you already know what a nucleophile and electrophile are. If this is the first organic reaction that you've been seeing, then you don't. So let's go over this. Nucleophile is abbreviated nuc, electrophile abbreviated E+. Just like the name suggests here, right? If you look at nucleophile, nucleo just stands for nucleus. And phile, right, you probably know means like love or has an attraction to or something like that, right? So these are nucleus-loving molecules. And if you remember, the nucleus just contains protons and neutrons, so the nucleus is positively charged. Now, if you're going to have a molecule or some sort of atom that's attracted to a nucleus, what charge is that going to be? Do you think it's also going to be positive? Is that going to attract you to a positive nucleus? Or do you think it's going to be negative? Would a negative thing be attracted to a positive nucleus? Right, and so with these nucleophiles, what you're going to see is these nucleophiles, they're always going to be full-on negative or at the very least partially negative. They're going to have some sort of negative charge so that they're attracted to that positive charge, right? They're always attracted to positive things, the nucleus, they're nucleus-loving. And that's going to differ from, if we go over here to electrophile, just to kind of contrast this now, electrophile, right, like electrons, and phile, right, meaning love. We all know electrons are negative. So the opposite is true for electrophiles, right? If you're going to have something that's going to be attracted to electrons, it better be positive, right? Because if it's negative, it's going to repel electrons, right? Like charges repel. And so our electrophiles, and you can see even up here, right, I put that there's a positive next to that capital E in the abbreviation. Electrophiles tend to be full-on positive or at the very least partially positive. Right, so they're going to have some sort of positive charge, either full or partial. Now, if I go back to the nucleophile side here, right, our nucleophiles, if they're negative, right, they're going to have electrons. Our nucleophiles are going to be things that want to donate electron density. And if you remember back to your old definitions of different types of acids and bases, that's what we would call a Lewis base, right? Nucleophiles are Lewis bases. These are Lewis bases, which means, right, that they're electron donors. They're electron donors, right? They're going to give electrons to that nucleus, to that positive thing. Now, in order to be an electron donor, you need to be sure that you have electrons to donate, right? So the types of electrons that we're looking for here are either going to be like lone pairs, right? We're talking about lone pair electrons, or at the very least, pi electrons. Or pi electrons, right? Because those are the types, like we talked about with like resonance structures and delocalization, those are the types that are relatively free, they can move around. We are not talking about electrons that are in sigma bonds, right? So the electrons that you can donate and move around in a mechanism, those are just lone pairs or pi electrons. So in order to be a nucleophile, you got to be negative or partially negative, and you need to have lone pairs or electrons. You got to have them. If we go over to electrophiles, Electrophiles are the opposite, right? If a nucleophile is a Lewis base, electrophiles are Lewis acids. These are Lewis acids, which means that they're electron acceptors. And in order to be an electron acceptor, you're either going to need to have an incomplete octet. So I'll say lacks a full octet. Or, and this may seem kind of weird because we haven't done these types of reactions yet, or it needs to be able to make space for electrons. That means either kicking out some really good group that can leave, or moving electrons around through resonance structures, something like that. So lacks full octet, or can make space for extra electrons. Right, you're not going to violate the octet rule. You're not going to have something that already has 8 electrons and now all of a sudden it has 10, right, for your things that can't expand octets. But you're not going to see some like carbon all of a sudden have 10 electrons around it. So let me give you just a quick example. Let's say we have, your classic, well, let's do an organic one. This is organic chemistry. Let's do an organic one. Let's say we have an alkene here, and I'm going to add an acid, just H+. And so if I take a look at these, I'll just draw the arrows. I'll just tell you what it's going to do here. Your alkene is going to go get your H+, right, so that you can add your H+, and now you have a positive here. I don't really care what the products are at this point. We're not talking about the organic reactions necessarily now. What I want to know is which of these two things here, right, I've got an alkene, and I've got the proton. Between the alkene and the proton, which one is acting as the electrophile? Right, remember electrophiles we said are going to be positive or partially positive, and they need to be able to accept electrons. And so sure enough, right, if I look at my proton here, it's got the positive charge, check. And if I look at the arrow, I have electrons going to the H. That means it's accepting electrons because it lacked an octet, a duet in the case of hydrogen, but it can take more electrons. So in this case, the proton is the electrophile. Right, so in this case, my proton's the electrophile, which hopefully means that the alkene's the nucleophile, but let's just take a quick look here. If I think my alkene's a nucleophile, that means it needs to have some sort of buildup of charge, which it does, right? It has 4 electrons here instead of 2, so it's got a higher charge density there. It's got it's got a buildup of negative charge there. And if you look at the arrow, right, the arrow is going from the alkene to the H, which means it's donating its electrons, right? It's donating these 2 electrons right here. Those 2 electrons are being donated to the H. Or one of them is. It's being donated to the hydrogen. So it is, in fact, acting as a Lewis base, or in other words, it's acting as a nucleophile. By the way, the only difference between a Lewis base and a nucleophile is that nucleophiles and electrophiles, they're always organic. Right, like I can come up with all kinds of Lewis base and acid examples that are not organic, but if it's organic, if it has carbon and hydrogen in it, then we call them nucleophiles and electrophiles, and they're just, well, yeah, we'll just leave it there. So here's an example of a nucleophile and an electrophile. So here's 7 more molecules, and I want you to tell me which of these molecules or atoms are nucleophilic, electrophilic, or neither. And one of these molecules is actually both. One of these molecules has an electrophilic spot and a nucleophilic spot. Now, if you're feeling comfortable with this already, this would be a good place to pause, take a crack at these, or you can, let me do a couple with you and then pause and see if you can do it yourself, right? It's going to be really important that you actually pause and practice this, right? In my normal class, that's exactly what I'd do. I'd put these all up and I'd let my students think about them for a while. So I'll stop talking for a second, then we'll go over them. All right, so hopefully you paused for a minute here. Sorry, I got distracted by a typo. This should be CH3. That's a methyl group right there. And so if I'm looking at these molecules, right, the first thing you want to do, and I'm sure I've said this before in other classes, but anytime you have something ionic, make sure you split this sucker up. So I'm going to have Na plus and OH minus, right? I've got my sodium hydroxide. And now when I'm asking myself about the which is electrophile or nucleophile, if I look at sodium, I'm really tempted to call sodium an electrophile because it's positive. right? It's positively charged. Electrophiles are positively charged. But what do I know about sodium? Do I ever see sodium ions, Na pluses, ever react with things? Are they pretty upset or are they pretty happy the way they are? Right? Sodium became positive because it lost that electron. It's got a full shell. It's super stable. It doesn't want to pick up more electrons. It's not going to pick up electrons. So it's not really an electrophile. This is just a spectator. So I'm going to ignore it, right? All those alkali metals, they're not going to be electrophilic, generally speaking. They're just going to be spectator ions. So I'm just going to label this as spectator. Which, again, you've been hearing that term since Gen Chem. Now with sodium hydroxide, I noticed that it does have a negative charge on it, which makes it look like a nucleophile. And if it's going to be negatively charged in a nucleophile, then I also need to make sure that it has some electrons to donate. So it needs to either have a pi bond or lone pairs. And sure enough, it does have lone pairs, which means that I know that this whole little molecule here is going to be acting as a nucleophile. Right? Sodium hydroxide is a good nucleophile. And we'll compare good versus weak in a future video. But it's nucleophilic because it's negative. It's got lone pairs to donate, right? It's a Lewis base. Now, if I go over to the next molecule, that butane there, I kind of got a problem because it's all nonpolar, which means it has no charges. Right? I don't have any partial positives or negatives anywhere, which means I'm just going to say that this is not an electrophile or electrophile. So not an electrophile or a nucleophile, right? You're not going to see butane be involved in any of these reactions. No nucleophilic or electrophilic anything. If I go over to my next molecule, I've got the cyclohexene. I said before that alkenes are a partially negative charge. They're a buildup of electrons. You have 4 electrons in between 2 carbons instead of 2. So, of course, there's more electron density there, hence the negativity. Which is making it seem more like, which you should be asking yourself, does that make it seem more like an electrophile or nucleophile? And hopefully you're thinking nucleophile because it's negative. And if it's going to be a nucleophile, again, you need to make sure that it actually has electrons that it can donate. And we said the 2 types of electrons were either lone pairs or pi bonds. And sure enough, we do have a pi bond there, right? So this also is going to be able to act as a nucleophile, right? And again, depending on what order you took these, you may have already learned all about alkene reactions in which you see them act as nucleophiles in every single first step of every single reaction. Right, because those electrons in that pi bond can go and get something positive. So how about the borane, the BH3 thing over here? If I look at borane, I look at BH3. I got small dipoles, real tiny ones, where I've got a partial negative, partial negative, partial negative, and a little partial positive on that boron. So if I look at the hydrogens, they're a touch negative, which makes me think nucleophile, but I don't have any electrons on them, right? I don't have any lone pairs. I don't have any pi electrons. I just have the electrons in the sigma bonds. So I know the H's are not nucleophilic. They do not have free or available electrons to go donate. If I look at the boron, that's partially positive, right? That makes me think maybe it's more of an electrophile. And if I look at boron, what's nice about boron here is that it doesn't have a full octet, right? I only have 6 electrons around it, not the 8. So it's definitely reactive. It definitely can accept more electrons from a nucleophile. So I'm going to put that borane here is definitely, all it can really do here is act as an electrophile. All it can do is act as an electrophile, specifically at the boron, right? The boron is the electrophilic atom. Now if I bounce down to the bottom left, we've got water, good old H2O. I can do the same thing, right? I'll put my partial positive, negative, positive. Hydrogens are positive in this case, makes me think electrophile, but these H's cannot accept more electrons. They're full. They don't have a weak bond that can break super easily, so they're not very electrophilic. They're just there. The oxygen, on the other hand, is partially negative, makes me think nucleophile, and it's got lone pairs, which definitely makes me think nucleophile, right? It's got lone pairs to donate, and it's partially negative, so water acts as a nucleophile. We'll talk about how it's weak later, but just for right now, it can just be nucleophilic. That oxygen in that water molecule is nucleophilic. Now, if I look at the quaternary ammonium thing, right, this nitrogen with the 3 methyls on it and the positive, first thing that jumps out at me is I've got a positive nitrogen, right? So I'm thinking electrophile. It's a full-on positive, so I'm definitely thinking electrophile. And I just need to make sure that that nitrogen can accept more electrons. But that nitrogen already has 4 bonds. It already has 8 electrons. And there's nothing on this that would be great as a leaving group. It can't accommodate anything else through resonance, can't break a pi bond or something like that. Not going to be electrophilic. This isn't going to be another neither. This is not an electrophile or a nucleophile. So I'll put not an electrophile or nucleophile at all. It's just kind of there, right? I can't have, if I imagine some sort of generic nucleophile trying to add to this, I can't draw the nitrogen with a methyl and a methyl and a methyl and another methyl and the nucleophile having attached, right? Because now that's 2, 4, 6, 8, 10 electrons around the nitrogen. That is a big no-no, right? We can't violate that octet rule. There's no orbital for it to go into. You're not going to see that happen. It's not going to be either one. And then lastly, we'll look over here at acetone or 2-propanone. Put my partial charges on here. I've got a partially negative oxygen and a partially positive carbon, right? Oxygen is more electronegative than carbon. And so if I look at the oxygen here, oxygen's partially negative, kind of like it was over here in water, and it has lone pairs to donate. So this oxygen up here can act as a nucleophile. So if you had some sort of electrophile, something electrophilic, that oxygen would be attracted to it, right? Something positive would be attracted to the negative on that O. But now here's what's kind of weird with this one is that if you look at this carbon down here, it actually is electrophilic because it's partially positive, so it's going to attract a nucleophile. But the issue here is that it actually can, sorry, did I say, what did I just say? It should be able to attract a nucleophile, right? If I have some sort of nucleophile that's like, say, negative, it's got its lone pair, this nucleophile can actually attach to this carbon. Not that the carbon can have 5 bonds, but it has a weak pi bond that can break, right? Imagine if we're doing resonance structures, right? It's easy to just move that pi bond away. That's not that big of a deal. That's a really weak bond. And so what you can do is you can get that nucleophile to add to that carbon and kick out that pi bond. And we are going to see a lot of that in the future where you attack carbonyls like ketones and aldehydes. So actually the molecule, this last molecule, has both a nucleophilic spot and an electrophilic spot, so it can kind of do both. It depends on what you add to it. If you add acids or H pluses, those are going to go on the oxygen. If you add something really negative, those are going to go on to the carbon. So hopefully you have a little better sense of what's a nucleophile or an electrophile. I have some practice and some extra things posted online. And yes, so in the next video, we're going to start applying this to the SN2 reaction. So look out for that. Happy studying and good luck.